Okay, here we are. We're looking at example 5. We are still in chapter 4, so we are looking at axial deformation. And we're just going to sum it up this time. We have PL over AE as long as we are in the elastic region. And if we're not, then we have to use a stress strain curve. So that just says that it is the MOE, but it's also for elastic. Okay, so we have a rigid bar. Okay, here's our rigid bar. It's supported by a pin-connected rod CB that has a cross-sectional area it's made from. Determine the vertical deflection at D when the load is applied. So you have to remember if we are in the elastic region, as we have just this slight rotation, the displacement we can consider to be in the vertical direction because there's insignificant in the X direction, which makes it a much nicer solution. Okay, so we're going to be looking at that vertical rotation coming straight down. So as I apply here, we have a pinned connection and we have a rod, a pin connected rod that is in tension. So as this stretches, okay, as this stretches with that rotation, if we can figure out what's going on here, then we can relate it to the end. So let's just go through and pick out what we know. We have a rigid bar by a pin connection, the bar area. So the area of the bar is given as 14 millimeters squared, which we can divide by 1,000 and divide by 1,000 millimeters per millimeter, so that we can get this into units of meters. It is made from this aluminum, and we can actually go into the back of the book and make sure we're in SI. And our modulus of elasticity was 68.9 gigapascals, which is 68.9 times 10 to the 9th Pascal, which is a Newton per meter squared. Okay, and we have an original length. Okay, so our original length, it's not given, but I can see that this is a nice, look at this, it's a nice right triangle. So it's going to be the hypotenuse of that geometry. So I have 1.5 meters squared plus 2 meters squared. And when we do that, we're going to get 2.5 meters, and that's our original length. Okay, so far we have E, A, L. In order to find that delta, we're going to have to find the internal force. So let's start with our equilibrium free body diagram. And we are going to note that we have a pinned connection. So we have a Y, a X. I do have this uniform load, and because we're just finding the moment that it creates and we're not worried about a shear or a moment diagram or internal force at a weird part, we can just reduce this to a point load. So the area under the curve, it's a rectangle, it's base times height. So I'm going to have 4 meters times 300 newtons per meter. And so I get 1,200 newtons, okay? Now this bar is in tension, so it's pulling back up, and we're going to have a force in member BC. And the nice thing about this being a 2-force member is that we know that it's a 1.5, so 3, 4. Okay, so 3, 4 triangle. We have 2 meters and we have 2 meters. So now if we sum the moments about point A, okay, I'm going to get minus 1,200 newtons times 2 meters. Plus, I just need the X component of this in order to get the member. I mean the Y component, and the Y component is 3/5, so plus 3/5 force BC, okay, times also 2 meters equals 0. So we can divide through by 2 meters, and that goes away, and we are left with 3/5 force BC equals 1,200 newtons. We can multiply by 5, divide by 3. So our force BC is, well, it's easier for me to divide by 3, which is 400 times 5, which is 2,000 newtons. So that's the force in BC. So if I know the force in BC, then I can actually calculate the change in length of BC. So let's go ahead and do that before we get into our deformations. So if the force of BC is 2,000, okay, then I know that the change in length of BC, because remember, as this rotates down, BC is going to stretch. So let's just go ahead and get that delta. Okay, it's not like it stretches if it's straight down and the 100% of that stretch goes down. It's kind of stretching at a weird angle. It's going to be stretching and creating, it's just going to be a little bit different. So let's just go ahead and get the final length of that bar. So we're going to have delta equals PL over AE. That internal force is 2,000 newtons. The original length is 2.5 meters. Okay. The area is 14 divided by 1,000 divided by 1,000. Okay. Times 68.9 times 10 to the 9th. And we can get a change in length of, so we have 2,000. 2.5 times 14, 1,000 divided by 1,000 divided by 68.9 e to the 9th times divided by. So if we are looking at meters, we get a very small number. We get 0.0051835 meters. So if I want to find then the total length, the final length of that bar, the final length of that bar is going to be the original length plus delta, because delta is change in length over length. So we have 2.5 meters plus that delta. So 2.5 plus, and I get that we have a final length of that bar of 2.505, I can't read that small, 1835 meters. Okay, so now let's draw what the deformation looks like. And this is where it gets a little bit tricky. We haven't done a problem like this. We haven't done a problem where we have like a weird triangle situation. So let's draw our original. And we know originally we have a rigid bar. And we know originally that this is 1.5 meters tall. And we have this original kind of bar right here, and that's 2.5 meters, and we know that this is 2 meters. And then we go to stretch. And when we go to stretch, when we load this down, it is going to want to displace down like this. And I am looking for delta D to D prime. Okay. And I know that I'm going to have a delta here. And when I look at this, I can actually go back and I can draw. Let's see if we can do this neatly with this pen. And I know that that stretch is going to look something like this. Well, if I could make it go to the point, okay? So it's come down, and I know that this length, this final length right here, is 2.5051835 meters. So what I really need to find is this angle kind of like right here. If I could get this angle and I have 4 meters and down in an angle, then I could calculate how far down we go. So I need this angle. I'm going to call this theta prime. Okay, and where does theta prime come from? Well, look at this angle. This could be theta prime prime. Okay, and so if I'm looking at theta prime prime, I also know as this rigid bar is coming down, because it's a very, very small rotation, this is still connected here at 2 meters. So now see, I have this nice triangle. And I know the side of 2 meters, a side of 1.5 meters, and a side of 2.505 blah, blah, blah meters. And if I know 3 sides, and I need to get an angle, I can use law of cosines. Okay, law of cosines. So law of cosines says, and this law of cosines is always on your exam, so this is fair game, is that if I'm wanting theta prime prime, then the length opposite of it, so here it's going to be that length final squared, equals length 1 squared plus length 2 squared minus 2 times length 1 times length 2. And then we have a cosine Okay, cosine the angle opposite of the side opposite of that angle. So that would be cosine theta theta. Okay, so I know length final. Okay, that is 2.5051835 meters squared plus, okay, not plus, equals, okay. Now I have 1.5 meters squared plus 2 meters squared minus 2 times 1.5 times 2 times cosine theta theta. Okay, so let's multiply this out and see if we can get cosine theta theta. So I still have that final length in my calculator. So I'm going to square it. And I'm going to square 1.5 and subtract it. I'm going to square 2 and subtract it. And now I've got to take this. So I'm going to do 2 times 2 is 4 times 1.5 times. And I get 6, but it's a negative. So I'm going to divide through by negative 6. 6 change signs divided by. And somewhere I've messed up. So let's do this again. 2.5051835 squared. Okay, 1.5 squared minus 2 squared minus 4, enter 1.5 times, change signs, divided by. Okay, and now I'm going to take the inverse cosine, and I get that theta prime prime is 90.24775 degrees. Okay, so if I know that this whole big angle is that, well, I can calculate then that theta prime is, okay, is theta minus 90 degrees. Okay, and that gives me 0.24775 degrees. Okay, so that little tiny, you wouldn't even be able to notice that. It's so tiny. So let's go back now and look at this triangle. It is 4 meters to the end. I don't know what D to D prime is, but I do now know that this little angle right here is 0.24775 degrees. Tangent of 0.24775 degrees equals opposite over adjacent. So we're going to subtract a 90, and I'm going to take tangent, and now I'm going to multiply by 4 meters, and I get that my theta delta D equals this very tiny number, 0.017296, and that's in units of meters. So let's rewrite that. Theta D prime. So we can multiply by 1,000 now to get back to millimeters. And I get 17.3 millimeters. And directionally, wow, that looks terrible, my friends. That looks terrible. Why does that look so bad? Why does it look so bad today? Let's see if we can figure this out. There's just a weird light in here, huh? Okay, so we get this displacement of 17.3 millimeters down. Okay, so like I said, this one was a little bit different because as our cable stretched, with rotation, before we've done cables that stretch straight up and down, so delta equals the change in length of that cable. This time, okay, we are stretching, but we have kind of this skew to it, and so it's getting longer in the both x and y direction, so I need to figure out this displacement down. And so I can then go back and I can start, okay, what are some rules that I have way back from trig? And I know that if I have a side and a side and a side, I can use law of cosines to calculate an angle. So I can get this big angle in here, subtract out the 90, and then I have. So the next problem that we're going to do, we're going to use law of sines. So I'm going to show you how to use law of sines. But this is why it's super important to be able to draw a deformation like free body diagram so you can see what you're looking at.